So we talked about the concept of a virtual machine. So the concept of a container is somehow similar to a virtual machine, but it's also very different. So when you approach the concept of containers for the first time, you may ask yourself, what the hell is the difference? And that's why it is, well, let's say, time well spent to talk about this a little further. So the main idea of a container is not only to provide a virtualized, machine that isolates your process and gives you a little environment to play with, being isolated from a container that's sitting next to it. That's still what it does to some degree, but already there are a vast difference between the virtual machine and the container. The way that containerization has spread in the past years is not driven by the fact that you can create a little virtualized something, because that's what virtual machines already covered pretty well. But the difference is that it introduced a way to standardize software packaging. So what I mean is, if you take a virtual machine image, the virtual machine image is somehow dependent on the underlying infrastructure or hypervisor or virtualization software. So on VMware, for example, you have what's the ending, VMX or something. So there's a specific file format for VMware, and if you go to Amazon, you'll have a different one. If you go to OpenStack, it might be a different one, and so on. So if you look at the challenge to describing a distributed workload and automate it in a way that you can spread and apply that automation to different infrastructures, you'll have the challenge that you'll have to create different container images in their various formats. And that's a pretty wasteful task. I would like to, as a developer, I'd like to eliminate from my value chain. So I would like to create something that I automate once and that I can deploy everywhere. So one essential part of the container concept is that there's a container image format that can be reused across a variety of infrastructures. In fact, there are different container formats, but by far the most popular one is the Docker container format. So let's consider for the remainder of the tutorial that the Docker image format is the de facto standard, and that it has spread so hugely and widely that we can assume that this is a common community standard, because basically that's the case. Maybe there's something coming up in the future. There are some standards arising, so the container format may change over time. But the main point is that once you created a container image, you can run it in any environment that is able to run a Docker image. And this could be a Docker on Windows, it could be a Docker on Linux, it could be a Docker on macOS, or it could be a Docker somewhere else. And as we will see throughout this training, it can be a Kubernetes as well, that uses Docker internally, or that uses maybe even Containerd or some other containerization technology that uses and supports the same container format. So I mentioned Cloud Foundry as a technology to create a platform as a service that's a bit more comprehensive than Kubernetes in some ways, but a bit more restrictive in other ways. And you can, for example, upload a container image there in the Docker format and run a container within Cloud Foundry. Although Cloud Foundry uses internally a technology called Garden as part of the Diego subsystem, which may be replaced with Kubernetes pretty soon, but you get the point. The container image is more than the container daemon, and the container daemon could be something else than Docker. As long as the container image is supported, you'll have a standardized way of creating a piece of software in a way that it is just like a real container used for shipping goods, standardized in a way that you don't have to care what's inside, but that all you need is the single command that can be used to start this thing up and create a process from the container image. So an essential part of containerization is standardization of software packaging in a way that it can be reused, and that it also bridges the gap between your local development environment, your staging environment, your testing environment, and your production environments. So for example, you may be developing locally using Docker or Minikube or any other technology like that. And then you deploy it to a production-grade Kubernetes cluster in production. So with coding with virtual machines, the question is, can you replicate the production environment somehow to your local computer or to your development environment? Or is there going to be a structural difference between your local environment and your remote environment? We are going to look into a paradigm called the 12-factor app throughout this tutorial several times. It's worth reading. So if you have a bit, spare time because you're under lockdown and you have no other hobbies, well, it's really worth reading through the 12-factor manifest at least once. So there are 12 basic rules, and one of them is here devprod parity. And devprod parity means that the system where you develop should be exactly the same than the one you deploy in production. So in this regard, a container helps to do that, because you can develop your container image locally and then use exact the same container image remotely. All right, question to you. Is that somehow, does that make sense for you, or is that too abstract or too esoteric for you to grasp? Did you get that standardization idea of a container? We'll have some, examples later during the training where you can see that in action, but so far, do you understand the underlying idea?
Yeah.
All right, perfect. So, standardization. Obviously, the other part of the containerization is that you'll create an isolated environment to shield a process from another process. So, I give you an example. We are, as my company is investing a lot of effort into automating the life cycle of databases. So we've created a technology that allows you to spin 1,000 Postgres clusters, where each cluster is a streaming cluster consisting of 3 virtual machines. So you have 3,000 virtual machines, and you need to deal with them automatically, obviously, because that's too much for humans to maintain. And each of the clusters, has individual virtual machines, and each virtual machine runs several processes. So what do you think are the processes of a database server? Any ideas? Well, at least one is obvious. So let's start with the obvious one. What is one of the processes running in the database server virtual machine?
Database management system, obviously.
Exactly. So, but this is not always sufficient. So in our case, for example, we have also a streaming replication with Postgres. Let's take Postgres as an example. Postgres does not come with a replication manager. It does come with replication. So you could have one Postgres server, another Postgres server, and transfer data so that the second server, the secondaries, will do exactly what the primary server does all the time. So you write to the primary and the secondary will read that. If your primary fails, you can basically point your application to the secondary and you'll be able to recover fast. So if you want to automate that, you need a cluster manager that will observe the master, and in the case that this thing will fail, recognizes that and make himself the new primary. So because it is problematic to do that with 2 nodes, because if you, for example, have a network segmentation where the communication between the 2 nodes is interrupted, they would each think that, oh, I'm the primary, and well, my secondary is gone, but the secondary will think my primary is gone, will try to become a new primary. So that's what they call a split brain situation, and a multi-master situation could occur from that, which is usually horrible because it can produce data inconsistencies. So in that particular case, you need to add a third node so that you have a cluster manager that uses a quorum, where a majority of nodes is in a network segment. So you have 3 nodes, and you assume that you can only cope with a segmentation between, one part of the group where there's always going to be a majority in some of the 2 partitions. If you, for example, have a network segmentation across all the 3 nodes, you're doomed. But, that's how it works. So the resiliency against a network segmentation in one of the 3 segments, usually called availability zones, will be covered. So you need a cluster manager observing the cluster. There will be a second process. If you want to have shipping of logs and metrics, you could collocate a log stash, which is another process. If you want to create backups and restore triggered by automation, you could have a backup manager. So what I'm saying is that on such a database server, it is very likely that there are several auxiliary projects, processes collocated. And the problem with that is that each of these processes could also turn crazy. So they could, for example, have a memory leak and consume the entire memory of the virtual machine, bringing all other processes to an end too. So one process can compromise other processes because they are not well isolated. Are you familiar with the idea of microservice architectures so far? Would be another question.
Not really.
All right. So in the past decades, it was quite common to write very complicated application systems and have these application systems as a monolith. Well, there could be modules in the code, so that from the developer perspective, there's a certain separation of duties within the modules, but the whole thing was written in one language and often used one persistency data service, such as a central Postgres database or MySQL database. If application development continues over years and the application code base grows and grows and grows and grows, at some point this becomes unhandy, because especially if your team also grows, let's say you have 50, 100, 500 developers working at an application system, like having a single code base is very tedious for various reasons, for scaling the team, but also because the certain aspects of an application system could come with very specific requirements, and these requirements, they'd be much better solved and implemented with a particular language. For example, if you need concurrency and good execution time, then maybe Go would be a good language, or even C++ or something like that. But if, for example, it is more about dealing with data structures that may vary over time because they are read from a document database, and you don't want to use a typed language there, maybe you want to use a language like Ruby. Whereas if you do streaming a lot, maybe Node.js would be nice. And the same would be true for the databases. So if you, for example, are mostly exchanging messaging information between various components, then maybe you want to use a RabbitMQ. If you want to store semi-structured data, well, a document store would be nice. Whereas transactions, asset-compliant transactions, require a relational database management system. So in these large systems, it is very common that you'll split them into little services, and they can be as much as orders of a shopping cart versus clients of a shopping cart. So there could be a client service, there could be an order service, and there could be a product service. And then the actual shopping cart could be a web application tying all those little backend services together with plenty of JavaScript. In order to deploy such a system, you'll have to, organize the deployment of each such a service. So how would you do that? And again, containers become in handy, because with a little service developed in a particular language, you can deploy such a thing in a container, and then you'll have a large number of containers that you'll have to put together. And this would be called container orchestration. So we'll come to that during the training, like several times, how the container as a standardized building block, allowing you to isolate, those processes being co-located, but also allowing to spread them across the cluster. So we can do both. We could implement a database in Kubernetes with some restrictions, but we could also deploy stateless web application parts of such a distributed system. They all would be little chunks of little processes cooperating, but still being shielded to some degree.